Today we begin our adventure into trigonometry. We're starting in chapter 4, and this lesson, 4.1, is really just getting us ready for what's coming next. In other words, it's a lot of things about notation and a hodgepodge of different terminology that's coming that's new to us. And so you're going to find that it's kind of like a hit and miss, a lot of different things. Take some good notes. I'm not going to do a bunch of each type. I just want you to start getting familiar with how we do things in trigonometry. Let's begin by looking at degrees. All right, degrees are a way to measure angles, and it's equal to 1/180th of a straight line. If you think of a straight line measurement, if that's an angle, which is weird because we're used to an angle being less than 180, but a degree is just one little tiny sliver of that, 1/180th. That's the measurement of a degree. Remember that we talked about how big a radian is. A radian is closer to 60 degrees, so it's a bigger unit of measurement. But today we're going to focus more on degrees. And as we do that, there's different ways to represent degree measurements. We can represent them as a decimal, and this might be a way that we're used to seeing. This is a degree measurement, so it's a little bit bigger than a 37-degree angle. But we can also write degrees and break down their part, like this is 42 degrees, but it's a little bit more. We can break it down into smaller increments. A degree can be broken down into minutes, and I missed my little double hash mark up here, and seconds. Think of it like longitude and latitude. That's how that is measured in degrees, minutes, seconds. It works just like a clock in that a minute is 1/60th of a degree, and a second is 1/60th of a minute. It works very similarly. The problem is that you can't do math very good with degree, minutes, seconds. We're going to use decimal values for degrees to do math, but we're going to be given degree measurements and probably be reporting back degree measurements in degree, minutes, seconds. We need to be able to convert between the two. Let's start with this first one. We have 37.425 degrees. This right here tells me that it's a little bit less than another half degree. It's 37 and almost a half, but not quite. If you think on a clock, half an hour would be 30 minutes. So this is going to be a little bit less than 30 minutes. The way to figure that is to take this decimal value and multiply it by 60. So I'm going to take 0.425 and multiply it by 60 and see what I end up with. And that is 25.5. Remember, we said a little bit less than 30. What that means then is that I have 37 degrees and 25.5 minutes. What I'm going to do now is take this 0.5 that I have left and multiply it by 60, because that's 0.5 of a minute. If I take 0.5 and multiply it by 60, that minute is going to turn into seconds. 0.5 times 60 is 30. So this is in minutes right here. This is in seconds. So to convert that, I'd come back and I'd say, all right, I've got 37 degrees. I've got 25 full minutes. And then I took that 0.5 and turned it into seconds. Now I wanted you to see how that works. And you can do it like that. If that makes sense to you and you like that, do that. Most calculators do have a nice conversion button for you to convert this to degree, minutes, seconds. And on our graphing calculators, if you do second apps, that's angle on your calculator, you can convert this 37.425 to degree, minutes, seconds. You type this, go to second apps, I think it's number 4, and press enter, and it'll convert it straight to this degree, minutes, seconds. You might want to pause the video and try that. That's kind of a handy button to have. And so maybe you'll want to do it that way. I'm going to go ahead and move on to the other direction though. What if you are given the degree, minutes, seconds, and you want to convert that back to decimal so you can do some math with it? There's not as handy of a button. It's kind of in that same spot on your calculator, but there's not a seconds button. There's just a degree and a minute, and you're kind of in and out of that. It takes a lot of keystrokes to go convert. So I'm going to show you how to do this, and it might be faster just to do it by hand, kind of like how we did it by hand over here. Notice that to convert 2 to the degree, minutes, seconds, we had to multiply by 60. What do you suppose we have to do if I want to convert the other way? Well, I'm going to divide by 60. My 42 degrees is fine, but this is in minutes, and it's a part of a minute. To find out what decimal part of a minute is, I'm going to take that and divide it by 60. But here's the tricky part. This is in seconds, and if I'm trying to go to straight degrees, I have to convert this into degrees. How many seconds are in a degree? Well, how many seconds are in an hour? Well, you'd have to divide it by 60 and divide it by 60 again. That's the same as dividing by 3,600. This is how I would enter this in my calculator. I would just do 42. Go ahead and get the degree measurement. Plus, I've got these minutes here. I'm going to take 24 and divide it by 60. And that's going to take the 24 minutes and turn them into a decimal part of a degree. Plus, I'm going to take these 36 seconds and divide by 3,600 and turn that into a decimal part of a degree. Press enter and you've got your answer. There we go. Not a real tricky thing, just something you need to be familiar with. One of the other things that happens as we start this trigonometry process and we start working with these angle measurements, a lot of it has to do with navigation. And when you are doing navigation, they keep track of their angles a little bit differently than we keep track of our angles. We think of a protractor, I guess, and think of an angle that starts over here, and then it's like going over here someplace, and so maybe that's like a 100-degree angle. That's how we've learned to measure angles. So we start looking, going to the right, and then we see how far this goes, going kind of counterclockwise around. Okay, that's a good way to think of it to do math, and we need to think of it to do math that way. But for some reason, navigation works differently. Pilots, so you'll see this with airplanes, you'll see it with ships, they think of everything in respect to due north. If you look at like a compass rose, you're starting right here, due north, and you are looking at where are you going with respect to due north. We look at, basically your angle is created by your line of travel and your due north line. So let's say that you are traveling over here someplace. The angle is measured from due north clockwise. So it's going to start here and it goes clockwise. It goes this way all the way around. And that is going to be the bearings. So this particular bearing, well, it went past 180 degrees, so it looks like it's about at maybe it'd be another 45, so 200 or 225 or so, like that's what those bearings would be, 225 degrees. That's how that angle is measured. Let's try this number 3 here that I have. It says, describe the ship's bearings from Cape Canaveral. Cape Canaveral is up here, so this is where I'm traveling from, so I put my little compass rose here, and then I'm looking, maybe I need to make that a little bit bigger, and I am looking from due north, so I'm looking right here's due north, and here's my ship down here, and I have to measure this angle right here. Well, that's about 90 plus another 45. I would say those bearings are a 135-degree angle. And of course, I'm just estimating those angles, but that's the way measuring bearings works. The problem is that we can't do math with bearings because we think of angles in this format. And so those would be different numbers, different angle measurements. We're going to have to be converting between the two to be able to take information, work some math on it, and report it back to the pilots. We've got to be able to work both ways with that. That's what, just be able to figure out those bearings. We don't have a lot of those today, but those kinds of problems will come. All right, here's the next new thing. We actually spent quite a bit of time on Friday, or on the last class day, whatever that was, working with radian measurement and figuring out what radians were. So this part should be review now from what we did on our last class period. A radian, this is to recap, remember that a radian is a unit of measurement for an angle, just like a degree is, but it measures differently. 1 radian is an angle measurement that is formed when do you remember? When the radius, so let's fill that in, when the radius is equal in length to the arc length. Or really, to be honest, I'd probably rather write that the other way, because the radius is sort of given, and then so it's when your arc length, because we started with our radius and then we started wrapping around, is equal in length to the radius. We took this measurement and then we wrapped it around the circle and it landed right there, and at that spot we created this angle, and this is considered 1 radian. Remember that we said it was close to 60 but not quite 60, and it doesn't have a nice conversion between radians and degrees. Let's practice some of those conversions. We will be doing a lot of this. This is how we started it. We used a nice proportion that we did have a clean conversion between, and that was that pi radians is the same as 180 degrees. And we use that to set up a nice proportion. Radians on top, degrees on bottom. So when I try to convert 50 degrees to radians, I put my degrees on bottom, my radians are on top. I'm going to take 50 times pi, set it equal to 180 times x. Something's going crazy there, sorry. I'm going to divide both sides by 180. And typically, we kind of like to leave pi in our answer because it's more exact if you're going to radians. Degrees, you've never had pi in your degree measurements before. We don't want to start now. But radians, we kind of do. That leaves it more exact. I'm going to cross out those zeros, and it's basically going to reduce to a 5 pi over 18. And we'll just leave that as the radian measurement. Likewise, I'm going to come over here and do it again. This time I'm going to convert radians into degrees. This time I know the radian measurement, so that needs to go on top, and I'm looking for the degree measurement. If you are given a radian measurement that doesn't have pi in it, that means that it's been rounded off. So this 3.6 is not an exact radian measurement. It's been rounded off in some way with it because it should have a pi in it. If they're going to go ahead and give it to me as a decimal, let's go ahead and calculate with some decimals here. You're going to see it kind of happen both ways, so I thought I'd try one of each. I'm going to do my cross products again. 180 times 3.6. I have 648 equals pi times x. Let's divide both sides by pi. And again, since I'm going to degrees, we don't typically leave pi in our answer in degree measurements. I get x to equal 206, let's say 0.3 degrees. Now, that's how we start. And then we start looking for shortcuts, because the reality is we're going to be doing a lot of this, switching between degrees and radians. Let's just cut to the chase. Let's look and see, what are we doing? To get from degrees to radians, it looks like we're always going to be taking our degree measurement, we're going to multiply it by pi, and then we're going to end up dividing it by the 180. Multiply by pi, divide by 180. Whereas to go from radians to degrees, we take our angle measurement and we multiply by 180, and then we divide by pi. So we're doing opposite things there. But we can make this a little bit quicker. Let's not have to set up this proportion every time for the shortcut. Let's jot it down in our notes so we can use it. To go from degrees to radians, you're going to multiply by pi, and then you're going to divide by 180. So we say we multiply by pi over 180. If you want to go the other direction, you're going to multiply by 180 over pi. Squeeze that word in there. I always remembered, for some reason, radian measurements oftentimes have pi in them. If I'm wanting to go to degrees, then I'm going to want that pi to cancel out. That's what I always remember. Pi is on the bottom because it's going to cross off with the radian pi that I have on the top. You'll see what I mean here in a second. If I'm trying to go to degrees, then I'm trying to gain a pi, so I want that pi to be on top so it stays there. Let's look at number 4. How many radians are in 90 degrees? All right, I have the degrees, I'm going to radians. I'm going to take 90 and I'm going to multiply it by pi over 180. I'm trying to go to radians, so I'm going to gain this pi. Think of this 90 as over 1. The 90 and the 180 are going to reduce. You just end up with pi over 2. And that should make sense because remember on the last class when we were talking about radians, remember that 1 radian is the same as 180 degrees. If this is 1 radian, it should make sense that 90 degrees is half of that, or half of pi. All right, let's look at number 5. This one, we already have it in radians, pi over 3 radians, and we want to convert that into degrees. I'm going to take my pi over 3, and since I'm going to degrees, I'm going to want that pi to cancel. Remember, I'm going to put pi on the bottom and my 180 on top. So I'm multiplying by 180 over pi. The pi's cancel. I have 180 over 3. That's the same as 60 degrees. One more. This one, I'm trying to do some different things. This is in radians also, 7 radians, but it doesn't have pi in it. Remember, that must mean that that got rounded off at some point. Okay, so that's a little trickier to see that I want my pi to cancel because it doesn't really have a pi. Same idea though. If I know the radians, then I'm going to multiply by 180 over pi. I'm going to degrees. I don't want to have pi in my answer. So when I do this, I'm multiplying straight across. So you just take 7 times your 180 and then go ahead and divide it by pi, and we will just estimate it at 401.1 degrees. Lots and lots of converting between degrees and radians. We're going to do some of it again on a problem later. Oh, okay. On this problem, in fact. Here's our next thing that we talked a little bit about, is that arc length. If you think about a circle that has a radius right here, and then when you create some angle, and it doesn't have to be 1 radian, you just create any angle whatsoever. Here's an angle. This is the angle. This out here is our arc length. It's along the curve of the circle. And this formula that we have here helps us find that length. You would have done this in geometry, but you would have done it differently because we were doing everything with degrees. We're going to look at this arc length using those radian measurements that we were just talking about. First of all, I guess box this in, circle this, do something to make this stand out. Here's your arc length formula. Let's go ahead and jot down what all of those letters stand for. S, for whatever reason, I don't know why, stands for arc length. The R is going to be the radius of your circle. And theta is your angle measurement. In geometry, we use capital letters to represent angles. In trig, we use Greek letters. This is spelled theta so that you pronounce it correctly. We use this one a lot. It's a very common angle or Greek letter that we use. It's theta. And it is the angle measurement in radians. It has to be in radians for this formula to work. That's the big kicker. If it's given to you in degrees, you're going to have to do some converting to be able to use this formula. Let's try a problem. Number 7 says, find the perimeter of a 60-degree slice of a large pizza. 13-inch pizza. When you buy pizza, if you ask what size it is, they're going to tell you what the diameter is. This 13 inches is the diameter of the pizza. We're going to look for the perimeter of this entire thing. Not only will we need to find the arc length, we'll have to look at the other sides as well to get the full perimeter. But let's start with arc length. In order to use my arc length formula, I need to know the radius, which I can figure out, but I need to know my angle measurement in radians. And I know my angle measurement in degrees. Let's do a quick conversion. First thing I want to do is take that 60 degrees and multiply it by pi over 180. The 60 and the 180 are going to reduce, and I end up with pi over 3 for my theta value. All right, got that. Step 2 would be to go ahead and use the arc length formula. S equals R theta. Looking for the arc length. The radius, if the diameter is 13, the radius is 6.5, and theta is pi over 3. I don't see any reason to keep this exact. I'm going to want to get an actual number for that perimeter. Let's go ahead and multiply that out and type in, I'm going to type in 6.5 times pi. I always use that pi button. Don't use your 3.14, just find your pi button. And then divide it by 3. I think that looks like a 5. Did I say 5? Probably couldn't read my own writing. Divide by 3. All right, so that arc length is 6.8. Now that's measured in inches just like the radius is. That's how long this little arc would be. But remember, we're looking for perimeter. Not only do I need to take that arc into account, I need to take these two sides. Well, those are just radii of the pizza, and those would be each 6.5. Step 3 is to take my 6.8, add the two radii, the 6.5 and the other 6.5, and I'm going to end up with 19.8, and that would be measured in inches. That's the perimeter. So several things that you have to think about as you do that problem. Let's try one more. This one says find the central angle if I already know the arc length and the radius. Arc length is 3, radius is 8. Solve it for theta. It's really just 3/8. Let's go ahead and get a decimal value for that. That's 0.375. Remember though that theta is in radians. If I was going to label this, and I should, that's 0.375 radians. And that's a fine answer. I'm not sure, it didn't really specify whether it wanted degrees or radians. Let's go ahead and just practice converting that now to degrees. What do you do to your radians to turn them into degrees? Do you remember? Multiply by 180 over pi. So 0.375 times the 180 divided by pi gets me 21.5 degrees. That's another option then. Those two are equivalent answers. Last thing, angular and linear motion. I think this is kind of fun. This will kind of review your chemistry skills here, I'm sure. You're going to do a lot of conversion, and you probably are used to doing conversion tables or whatever you call them in your chemistry class. But in trigonometry, we're going to be dealing with angular speed and linear speed. Those are two different things. Angular speed measures things that are spinning fast. Those are typically measured with revolutions per minute, per second, I don't know, revolutions per minute, we'll say. How fast is something spinning? But linear speed is measuring how far you're going in a straight line. So that's more like when you're driving your car and it's miles per hour, something to that effect. Sometimes we need to connect the two, so we're converting. Today is a day of conversions, huh? One thing that we have to keep in mind, though, as we try to convert between these two different types of speed, is thinking about how far would you travel in one revolution of a tire. Almost think of it like you're riding a bike. So you're sitting on your bike and you pedal just enough to make your tire spin around one time. How far do you think you would have traveled in a straight line? Well, it's going to be whatever that distance around the tire is, that arc length. Well, that arc length, when you're talking all the way around the tire, is actually your circumference of your tire. So in this box, this is the big conversion that's going to be new for us. One revolution of your tire is equal to the circumference of your tire. I'm going to abbreviate that. I'm going to run out of room. It's equal to the circumference. And do you remember your formula for circumference? You can write it 2 pi r, or you could write it pi d. Either one of those works. We're going to use that conversion at the end of this example. Let's try it. This, number 9. A car is moving at a rate of 74 miles per hour when the wheels of diameter 2.7 feet. Find the number, that seems like a big tire, but whatever. Okay, it's a monster truck. Find the number of revolutions per minute the wheels are actually rotating. If you're going 75 or 74 miles per hour, I'm going to say they're going pretty fast. How fast, though? Here we go. Start at the far left because it's going to take some space. And you're going to write what you know for your current speed, and that's miles in 1 hour. Now, the problem with these types of problems is that you've got units all over the place. You're measuring your linear speed in miles, but you have your diameter measured in feet. We've got to get these to be the same units. Over here, we are in hours, but down here, you're wanting it to be in minutes. We need those to be the same units. I take these measurements and I convert them to these. Let's start by getting rid of those miles. Since miles are on top, I'm going to put them on bottom so they cancel out. And I'm going to convert it to feet. But you have to know the conversion between feet and miles. And you may or may not know this, but before this is all said and done, you're going to know that there are 5,280 feet in 1 mile. What that allows us to do is cancel out the units for that. And so we are now in feet per hour with this measurement. And the feet are good, but I would like to be in minutes. So I'm going to get rid of my hours. Since hours are on bottom, I'm going to put them on top and convert them to minutes. And then you should know that there are 60 minutes in 1 hour. Hours get to cancel out. And now I'm in feet per minute. But that's not quite what I'm wanting. I want to be in revolutions per minute. Now I'm ready to use my new conversion. I want to be in revolutions, so I'm going to want revolutions on top. So we remember 1 revolution is the same as my circumference. My circumference is 2 pi r. 2 times pi times my radius. Be careful, this was actually a diameter here. The radius would be 1.35. Could have done that pi d, might have been easier. About half the time they give us radius, half the time they give us diameter. So whatever works for you. To solve this problem now, I am going to be, and keep in mind, and I should have written this is 1.35 feet because those feet are going to cancel and now you're going to be in your revolutions per minute that you want. But we got to do all the math first. To type this in your calculator, you're going to multiply everything straight across on the top. And then you're going to divide, but it's going to be important that you insert parentheses because you're dividing by all of this stuff. So I'm going to divide by, and open parentheses, 60 times 2 times pi times 1.35. And then close the parentheses. And I end up with 767.7, and that's revolutions per minute. That's how fast the tires are spinning. Let's try one more. This example goes the other direction. We know how big the wheels are, and we know that the wheels are rotating 630 revolutions per minute. We want to find how fast the car is going, or the truck, in miles per hour. It's just like the problem we did, only you're going to go backwards. You're going to start with your revolutions per minute and turn them into miles per hour. What I'd like you to do is go ahead and pause the video and try this one on your own. And after you've tried it, then come back and you can check your answer. All right, this is what I have set up. Check your work. You maybe don't have all of those conversions in the same order. That doesn't matter at all, as long as you're getting everything to cancel and get yourself down to miles per hour. All right, check it out and go give that homework a shot. Good luck.